Hi and welcome. So I had to do a little bit of work on my car this last week, and I ran across something that, as an engineer, every once in a while you run across something that is so elegant and wonderfully creative in design that you kind of take a step back and go, wow, that was truly inspired. And I have a Kia Soul, and I had to replace my rear gas shocks. And I didn't ever really think much about them on how they worked, but it turns out there's a lot more to them than one might have imagined. These are the factory originals that came with it, and the welding on them is really nice. The rods are hardened and chromed, and the end piece you have to tighten a nut, a locking nut on here. These came with nylon lock nuts. So you take a wrench on this part and another wrench on the nut, and you tighten it down on the shock tower mount, whatever you call the piece that it mounts on the top. In any case, these are hardened, and I replaced it with ones that were best rated on Rock Auto. They were Monroe. I believe they're made in the United States. And in every way, from outward appearance wise, they were inferior. The welds were really poor looking. These look like they're robotic welds and very clean. The paint was inconsistent across the Monroe shocks and missing from parts down by the welds, and they were already rusting, brand new, right out of the box. They came in a box, each one. The shafts did not, at least around where the threads were not anywhere near as nice as these threads, and it was soft, and the wrench just rounded the end right over, which just totally surprised me that they were that poorly made. I was very, I'm hoping that internally they saved all of the best parts for the internal section, and it'll function wonderfully for years, but I don't have high hopes, to be honest with you. And they were the most expensive ones they had on Rock Auto for my car. They were the Monroe Performance ones, which I don't know. I got to give them a huge thumbs down, at least as far as fit and finish is concerned. Even the holes where the bottom pin bolt goes through, not great. But what interested me was I decided to look these up on how they function, and they are absolutely surprisingly complicated but elegant all at the same time. So inside you have a sealed cylinder. It's actually sealed on both sides, and they can be pressurized anywhere up to 2,500 psi, which makes them little bombs. So you don't want to just discard them as is. Inside is a piston, and right now that piston's all the way over here because this guy is pushed as the piston's all the way out. So here's the piston in there all the way, and there it is going back out again. Now here's some of the creative bits about this. So the piston right now is all the way at one end. There's 3,000 psi and some oil, some hydraulic fluid in here. And when you push this down, it's a sealed container. So the only way this moves down is they've either drilled a bypass hole through the piston itself, or they relieve the outside edges of the piston with little tiny grooves that the air and oil inside here can slowly go through and bypass. But then, how is it that when you push it in, it wants to go out every time? Because when the piston's here, the pressure on both sides is equal, right? And that's absolutely true. The pressure is equal on both sides. But as you push this in, right now with the piston over here, this is just an open cylinder in here. As the piston goes down, part of that cylinder is taken up by the rod on the other side, the push rod. And that rod takes up space, which increases the pressure on both sides. So as this goes down, the pressure increases all the way to a maximum at the bottom. The larger diameter of this rod, the more the pressure goes up as you push down. Now, that still doesn't answer the question as to why this piston pushes itself back out again, and that is really creative. If I draw a picture real quick, you have the sealed cylinder here on both sides with seals on one side where the rod goes through, and the rod goes down to the piston in the middle, maybe with a hole relieved in it, or maybe it is one of the ones with the edges that has little grooves in the edges. But in either case, the pressure here and the pressure here, P1 is equal to P2. So why is the net force going in this direction? Well, it wasn't immediately obvious to me until you think about it. So pressure is force per area, right? Pounds per square inch, kilograms per cubic meter, grams per cubic centimeter, force per area, right? So if the pressure is equal on both sides, let's say that this circular item is exactly 2 square inches, okay? So if I have 5 pounds per square inch, and there's 2 square inches of surface area here, there's a total of 10 pounds pushing in this direction. 5 pounds per square inch times 2 inches squared, the units cancel, leaving me 10 pounds of force, okay, in the English unit system. Now on this side, this is interesting. This bar is taking up some of that area. So let's say this is 1.5 square inches. Inches squared, just draw it that way. So this side also has 5 pounds per inch squared times 1.5 inches squared. This works out to 7.5 pounds of force. Now, if I have 10 pounds on this side, 7.5 pounds on this side, the net force is heading in this direction, 2.5 pounds positive, right? And as this pressure goes up, there's the force on this side will be even more than the force. It'll always be more than the force on this side. And as you push it down, the force will increase slowly. And it could increase a lot. If this was a really large diameter, if this was like 90% of the volume here, the pressure differential would be substantial. So they can tune these to work that way. And then to stop it from moving quickly, they fill it full of hydraulic fluid. And so that hydraulic fluid has viscosity, which only allows it to go through these grooves or the relief hole so quickly, and they can tune those holes or groove size to get the dampening they want in the cylinder. Absolutely fascinating. It's sort of an all-in-one design. They didn't need to do anything to keep the piston always wanting to be pushed out the opposite end because of this pressure differential that's built into the design. And that is, to me, as an engineer, is a really elegant design. So why don't we head over to the lathe, and I'm going to pop one of these guys open now. With 3,000 PSI, these are a bomb. And one of the recommended methods, even from the manufacturer Monroe, for some of their other pistons, is to drill a small hole on this end. And that will relieve the pressure safely. However, I have concerns because there's something called hoop strength. And hoop strength is the force pushing along this outside circumference all the way around the circle. The inside pressure is trying to make this thing expand, and what holds it in is this hoop strength going around the end. Well, when I drill a small hole, the hoop strength around that little section is going to be weakened, and this could explode. So don't do this at home. Highly recommended that you do not do this at home. This is definitely a risky move to open one of these. 3,000 pounds per square inch. If I have 1 square inch, there's 3,000 pounds trying to push this piece, this 1 square inch piece, right at me and have it fly off in this direction as quickly as it possibly can. 3,000 pounds generates a lot of acceleration, which makes it a bullet. So one way to get around this really large pressure differential, atmospheric pressure versus, say, 2,500, 3,000 PSI, is to use a very small drill bit, which is what I intend to use. Number one, that will minimize the damage to the hoop strength around the circumference here. Number two is the amount of force applied coming out of this hole will be smaller because it's pounds per square inch. So if I had a hole that was 50 thousandths of an inch in diameter, if the diameter was 50 thousandths of an inch, the area is pi r squared. So let's call it 3.14.025, half the diameter is the radius, 0.025 squared times 3.14 is approximately 0.002 inches squared. 3,000 pounds, 0.002 times 3,000 pounds is only 6 pounds of force. So 3,000 pounds per inch squared times 0.002 square inches. These units cancel, leave me with 3,000 pounds times 0.002, leaves me with 6 pounds of force. That is a very manageable amount of force coming out of that hole. So I'm going to drill a small hole, let the gas out, and then we will open this guy up, and it's probably going to make a big mess. But I really want to see what's inside, and hopefully you do too. Okay, so I'm going to stand behind this piece of Lexan. I've got the gas cylinder supported with the jaws of the chuck. So they're going to help to keep the cylinder together if it wants to rupture. I'm going to sit behind this piece of plexiglass, or actually Lexan. I'm going to drill about an inch up here. There's a little 16th inch drill bit, and there it is. Thank goodness that was a little less, it was a little anticlimactic. I was worried that this was going to be really ugly, but I'm surprised it sprayed any fluid at all, because all the fluid should have been on the bottom of this thing. All the hydraulic fluid should have been down towards the bottom, but it still managed to end up at the top. That hole size was only a 16th of an inch, so about 62.5 thousandths across, on purpose, because I really didn't want to risk having this thing blow up somehow. So next step, I'm going to drill a couple holes, drain most of the fluid out, if not all, and then we're going to part off the end here so we can see what it looks like inside. So we drilled another small hole in the bottom. I don't know if you can see this. So here we've got oil draining out, and I've got it draining into a couple absorbent mats so it won't make a huge mess. There's a surprising amount of fluid in there. Some of these supposedly just have a little bit of hydraulic fluid as a lubricant. These seem like they have hydraulic fluid in quantity. That's really quite an amazing amount so far. By the way, the inside of these, the gas that's pressurized in there is usually dry nitrogen. Nitrogen composes, a large percentage of our atmosphere, so it's not a pollutant in any way, shape, or form. Dry nitrogen doesn't have much water in it, so it won't cause rust and oxidation inside. So it's a big plus all the way around. Another thing I'm really curious about actually is how thick a wall does this thing have? So we're going to go kind of slowly here. And there we are. It's really surprisingly thin for such high pressure, right? It looks like this end cap here, they press fit in an end fitting and then welded it in place, which is kind of interesting. Check out how thin a wall it is. Who would have thought for this high a pressure, and it could be lower. Some of these are only quite a few hundred PSI, so maybe that's what this one was, but still, that's a pretty thin wall. About 50 thousandths. Alrighty, so this is a little different inside than I was expecting, not that I knew exactly what to expect. So this end has the rubber bushing for the vibration reduction mount to the bottom portion of the shock where it mounts to the wheel. And pushing the piston out, there is some sort of weird internal piston assembly. I'm actually a little curious here what that's all about, because see the piston rod? It's actually not coming out all by itself. We might have to take this over to lathe and cut the second section here as well. It's really weird. I don't know what's going on with it. So I might pop this in the lathe, and I'll just part this end right off here as well. So this gets curiouser and curiouser. So I parted this end off here, and lo and behold, inside we have a whole nother assembly. So this part, it looks like, was for pressure containment. This part was for a sliding surface where they could control how smooth the inner surface was. So this, see, is this rolled and welded or is it extruded? It is rolled and welded. Yeah, you can see the seam. I don't know if you can see the seam, but there's a seam right here where this was rolled and welded. So that's not terribly round. So if you want to make an accurate piston, you need to do something else. So I'm guessing that's what this solution was. And then the pressure was contained there. This looks, yeah, I'm not even quite sure about that. I think next up, I'm going to pop this over. I'm going to part this section off as well, right about here. And I'll be right back. Alrighty, so keeping this in order, this is the side that was attached down here. I've kept it all sort of laid out how it was put together. And so I parted this section off, and here is where the piston assembly is. And I'd love to see how they did the seals on this side, but you can't really see them. Maybe there's a burr on the inside. Let me deburr the inside to see if I can get this thing out. Okay, here we go again. So let's see if we can get this end out. And there is the magic. Boy, multiple levels of seals. This is a lot more complicated than the simple explanation I was giving. This really is a nice fit. And you know what's interesting? This is welded tubing too. I never would have imagined, but I guess they ground the inside of it. Kind of looks like it's a very nice fit here. It's all the metal filings. So it looks like there's multiple levels of piston here, and maybe that helps control the dampening just the way they want to. I can't exactly see. This was just a burr that I took off the end, but I can't exactly see where the bypass was occurring, I guess, around the inside of this rubber bushing here, because there is a metal seal there. We can pop this in the vise and unscrew this guy here. Sorry, I don't know if you could see that. So I don't know. So there's multiple levels of piston action, because there's ending up with oil and air behind here. And as this moves in and out, it's got to press past this section, but it also has to press past this section, and then even further limited by the very, very small opening around this end piece on the end here. Again, only allowing a little bit of air. So I think that's how they controlled the dampening very carefully on this guy. Because not only are you pumping the air through, but you're pumping this hydraulic fluid through, which is reasonably viscous. Certainly a lot more viscous than the air, which also incidentally behaves like a fluid. So let's pop this in the vise and take this end off. Okay, so I started loosening this guy. This is fairly soft metal. It wanted to roll over kind of easily, and there might be some sort of Loctite-like compound on it. Or they peened one edge over. The threads are really nice though. You can feel them. So there's another piece that the spring pushed on. So it's this order here. Yeah, there's this thin metal piece, which if there's high enough pressure would cause it to form a little bit and let stuff bypass it. And and then there's holes straight on through. And the holes are sort of sealed by this guy, as you can see. Just the center and the outside, but the holes are exposed. This is surprisingly hard rubber. Another washer lined up there. Then this hard, very hard plastic or rubber. I'm not sure what it is. And this seal, and another spring, and a final bushing that goes on the back, and all of that sits up against here. So check out the machining of here. Look at how beautiful those threads are. This is just gorgeous the way they did this. So this piece is pressed on, so it's going to be hard to get off. And until I get that off, I can't get this off. I'd love to see the seals on this end too, because the seals on this end, you know, have to keep the air contained in here at whatever the pressure is, 3,000 psi, 2,000 psi, 750 psi. Any air that bypasses that will, you know, slowly leaking out of this cylinder will cause this thing to fail, which is probably why these things wear out. I mean, I assume sometimes that this part would wear sliding up and down and let too much fluid by, so there wouldn't be enough dampening. But if this end goes and the pressure leaves, then they won't even go back up again on their own. So that's probably a problem. Let's see if I can press this piece off in the hydraulic press. Okay, so we took that little burr off, and I cut a little material off there. I suspect that's going to be pretty tight. So the seals are really interesting. They were pressed in here with massive amounts of force, and it looks like there's some pressure bypass holes there, maybe to force something against something in there. I can't really tell. You can see there's some green plastic in here that does not look particularly good health, and maybe it lets some of the air pressure out over time. Very interesting. Alrighty, so I went and took the other shock apart so you could see the whole assembly as one piece here, and you could see how the parts on the slide went together. So first thing I was thinking of while I was looking at this more was that the reason why they have an inner cylinder and an outer cylinder is because the shock is right next to the tire. So if some piece of road debris shot up and hit the side of the shock, it could dent it, and that would make it so the piston wouldn't run freely anymore if the outside cylinder was your guide for the inner piston. So instead, you have an inner piston that is offset by about 1/4 of an inch aside from the outer. And the outer can take some damage before this guy ever gets hit, all the while allowing the piston to slide smoothly up and down. Furthermore, I talked to a guy in my shop who is a car fanatic and big into racing, especially Formula One. And although I know he's a secret NASCAR lover at heart, but he pointed out that shocks have to operate in 2 different modes. When you're moving at slow speeds, the energies are much lower, and you want the dampening to be fairly slow, and you don't want this fluid to slosh by very quickly. You want the wheel to stay on the road. But at high speeds, the energy is a lot more, and the fluid needs to come through a lot more quickly to have dampening and to allow this to move at all. So there's 2 different modes they had to plan for this, and I'm wondering if part of it was this section back here, because this outer metal part is a very close fit to the cylinder, along with the rubber wiper that goes with it. So that's going to allow gas just to bleed by it a little bit as it goes, along with this very complicated section here. So you've got this nut that pushes on a spring that preloads this metal bushing right here up against this rubber seal along with the washer, like this guy. And that pushed up against the inside of the piston, and the metal part pushed against a washer, so I guess so that it wouldn't damage the piston like this. And so that would allow pressure to go by if you could exceed, probably in this direction, I'm guessing, if you could exceed the force of this spring pushing on that plate. And then in the other direction, maybe that's what this guy was for. Maybe that was the control the other direction. I'm actually not entirely certain. You've got this guy that directs the liquid and gas to the center. You've got its spring-loaded piece that fits on the back here, and then a bushing that pushes on that whole assembly. And again, this nut that you tighten here preloads that whole assembly. Kind of interesting. I was looking more closely at this guy, and in this direction, fluid can go through these holes, press past this spring-loaded assembly here that seals on the inside. Coming back the other direction, there are holes all the way around the outside of this guy, and this spring-loaded piece here presses against that with this spring and this washer assembly. So the combination that damps it in both directions. So the spring load, the force on this guy is set also by the same spring on this side and nut assembly right here. So this guy controls both directions of fluid and gas flow, which is a pretty creative design. So I'm guessing that maybe, I don't know, maybe this is the low speed, this is the high speed, because at high speed, even if there is a little bit of a gap here, trying to push a viscous liquid through a fairly small gap is going to put a fair amount of resistance. At low speed, you want this to be able to move a little bit, and maybe that's what this guy's involved, or maybe they work together. And then also, the whole assembly has some sort of loose seal on the end here that lets liquid go out, which is kind of interesting in and of itself. The seal on the end, I took this over to the mill, the other one, and I machined off the top part of it. So it had a plastic cover on it, and it had an inner seal that was not inside the piston, but inside on the bottom of the top of the shock. So over, oh, actually, you know what? It is on the inside. I'm correct. Stand corrected. It goes in between this guy and this guy here. And there's a wiper on the outside that was mounted to a piece of steel that was press fit into this assembly. You can see there, hopefully. There is another let me get my words here. There's another springama thing inside there that I guess is also a wiper of some sorts. And then a bronze bushing that I think is doing all the work of the seal. It was a really close fit to this rod. And I thought these were chromed rods, and they might still be, but I tend to think that they were just hardened. Not 100, well actually, you know what? You can see the chrome, so I guess it is chrome, because this is a different color than the inside of the shaft here. I don't know if that you can catch that on camera. This is sort of yellowish, and this is very silver, like chrome, white silver. So I think that's about what happened there. I thought that these, at first, these might be pressure inlets to push on a seal on the inside somehow, but they are not. Maybe they were how this part was mounted, or the fixture that went in, because this metal piece here, this outer housing, just got crimped over this whole assembly here. And the bronze bushing is press fit in as well. And that's about it. I wish I could explain some of the finer details of this, like how it differed at high speed and low speed, but I'm afraid I'm a little bit out of my depth. But it was an interesting disassembly anyways, and I definitely learned something, and I hope you did as well. Thanks for watching. Hope to see you next time.